okay? Which is, I believe, where we actually ended. This is the process that you should be moving through. Identify what you want for your answer. Identify what units you are given to start with, and then start a conversion process. Okay? A mantra that has worked in the past, if we were to write this out a little bit more generically, our first step is to write down what we want. Okay, so our want units. Our second step would be to write down what we have as units. And then in between, we need something to establish how those wants and haves disappear. So my have units would need to go into the denominator. My want units would appear in the numerator, which means we'll constantly be dealing with fractions. This would be a relatively simple conversion. This was a one-step conversion. The want disappears, and the have disappears, and I get what I want. Okay? Does it always happen that way? No. Probably what will happen is we'll have 2 units. Okay, so then what do we have to do? Our have 2 units and our want units. Okay? So the process is always what you have over what you want, what you want over what you have. Okay? The thing that's nice about this process is that it always works. Okay? In physics, you're told you have to memorize formulas. You don't have to memorize formulas. If you know the units, it's this process. Okay? So it all works out. This works in life too. Okay? A lot of people want to become nurses. Okay? Are you starting as a nurse? No. So what do you have? You have the desire. What do you have to convert that desire into? School. Okay? So you're going to convert that desire as a have, okay, into a different have. The education. Okay? Passing a class. Okay? You now have a new have. So what do you do with that new have? You convert that class, okay, into a degree. Are you a nurse yet? No. So what do you have to do? Convert that degree into experience. Okay? What do you do with that experience? You convert that into a nurse. Hey, now you're a nurse. Simple. It was only 4 steps. Why don't we have more nurses? Okay? Some people laughed. Okay. Okay? That process is something that we have to constantly cycle through. We don't just say what we want and all of a sudden it's there. We have to work through individual conversion steps along that process. Okay? So it will be a challenge. You have to think through each of those stages and decide what happens. Okay? You may decide that can't happen in one step. Okay? So you do a new thing to get around that. Okay? The next kind of fun part that's associated with this, remember when we did the conversation? 1,000 meters equaled 1 kilometer. Does that ring bells? Yeah. This works better if we talked about it in the same day. But we converted that into 1,000 meters over 1 kilometer, right? What did we say that equaled? How do I get the blue to turn into the black? What did I have to do? Divide both sides by 1 kilometer, yeah? So that piece is now right there. What I'm asking is, what is that piece? It's 1 kilometer over 1 kilometer? Yes. And it's 1. All of these conversion processes, all you're doing is multiplying by 1. Sometimes they're more difficult in life, which means you may not be multiplying by exactly 1. Okay, so your life may detract from that end goal. Okay, what we're trying to do is make sure that's as close to 1 as humanly possible for everyday life. For science, it gets to be exactly 1. Why? Because science is perfect. Life is not. Okay? Deep. So, that's what happened when you punch the computer. Some mathematical notations. Did we talk about this? No? Okay. So let's real quickly look at this. This is a simple thing, a little trick. Some people may like it, some people won't. If you don't like it, don't worry about it. Okay, what did the plus and the minus mean? Positive and negative. They also mean something else. If I had a number line with 0 and a +1 and a -1, what does the plus and the minus mean?
Distance from 0.
Direction from 0. Plus would mean moving to the right. Minus means moving to the left. The sign is telling you the direction you're going. That's it. Okay? That's what it means. If we go up to 10 to the +2 versus 10 to the -2, that can become a little bit more challenging to manipulate, but it's still the same idea. 10 to the +2 means do that calculation exactly where you've written the numbers. Where have you written the numbers? Someone caught on to it? Somebody recognized the fine line between a numerator and a denominator? Somebody else recognized that one? Okay. The 10 to the second is written in the numerator, so my calculation becomes 10 to the second, which is, that's 10 times 10. That would be 100. What does 10 to the -2 mean? Run that calculation in the denominator. What was the calculation? 10 to the 2, which is equal to 1 over 100. This allows you to swap calculations up and down from numerators to denominators, which becomes very handy considering that nearly all of our conversions involve unit analysis and dealing with numerators and denominators. If you don't want to deal with that, that is quite all right, because we have a device that does it for us. Like, really? It's called a calculator? Whoa, there we go. Someone is humoring me. Okay? A calculator will run that calculation for you. You don't have to think about those manipulations. If you're going long distance towards like med school, they expect you to do those kind of mathematical magic things in your head to simplify calculations. So be aware of that depending on your potential trajectory. Okay? Why does this come in handy? When I told you to memorize centi, what did I say it was? I did not tell you it was 100. What did I tell you centi was? 10 to the -2. Okay? Centi meant 10 to the -2. So when I look at my conversion, I get 1 centimeter equals 10 to the -2 meters. Why? Because that centi part right there is 10 to the -2. So that's 10 to the -2 meters over, wow, 10 to the -2 meters. Okay? You're like, ah. And the angel spoke. There it is. Okay? That's where it came from. We could have just as easily flipped it around and done it the other manipulation. But you just heard somebody else shout out, 100. 10 to the -2 isn't 100. Okay? What did they do when they were talking about that 100? What are you saying? You were saying 100 centimeters was equal to 1 meter. Is that wrong? No. That's the exact same as what's written above, except what did you do? You said run the calculation of 10 to the second in the opposite location. Where is it currently located? In the denominator. So what am I going to do? Put it into the numerator. 10 to the second is 100. There's where it came from. Why would you memorize 100 centimeters is 1 meter as opposed to 10 to the -2 meters is equal to 1 centimeter? One is simpler. Simpler for who? Simpler for your brains? So when you take a test, you're only using your brain. You're like, yes, I only use my brain. You don't use that calculator that we just talked about, and you're all like, ha, ha, ha. Okay? Why were you told to memorize 100 centimeters to 1 meter? Because people thought your puny little brain couldn't deal with powers of 10. For the record, it can't. Okay? So we changed it to this, okay? So that made it easier to memorize. Well, why did they tell you to do that? Well, because their human brain sucked at it. Why did they memorize it? Because their human brain, their teachers all the way back couldn't deal with it. They went all the way back to the point where, what did they not have? A calculator. Do you have a calculator? Yes. You don't need to memorize this piece of information. Because believe it or not, 100 centimeters to 1 meter is actually more information than 10 to the minus 2 meters is 1 centimeter. You're like, bull crap. Entirely true. My power of 10 goes with the core unit. Okay, what did I say milli was?
That would be
10 to the minus 3. Okay, and I just heard someone say it's 1,000. Yeah? You're like, Mike, you're digging a hole. Kilo. What does kilo mean? And what are you going to memorize down here? 1 kilometer is? Okay. You start changing where you're placing your numbers. And I did that middle one wrong. Your power of 10 in the purple one is located where? Okay, in your cheat method, because your brain couldn't deal with powers of 10, you put it next to centimeters. Where did I place it? Next to the core unit. Let's move to the red one. Your human brain couldn't deal with 10 to the negative 3, so you converted that around so you could put it next to millimeters, right? What happens when we move to kilo? Where did you place your multiple? Don't focus on the denominator. You placed it with a different unit. Everybody see that? Power of 10, complex unit. Complex unit, simple unit. Look at the method I'm telling you to memorize. Where's your power of 10 go? Avoid top and bottom. It goes with the core unit. When? Every single time. Those being like, my human brain can deal with changing where that power of 10 goes. Cool. When you get it wrong, I'm going to be like, remember how I told you that your brain couldn't do that? Okay, when you get it right, you can be the same back to me. You remember how I said my human brain was better than yours? Yes, you're right. You win. Okay? But that power of 10 will change places if you don't use it as I'm telling you to memorize it. It is a very subtle change, but it's a change that is significant enough that will take a right answer to becoming entirely wrong. Okay? Because you're changing the placement of your number, of the power of 10. It's either going with the core unit, okay, or it goes with whatever unit you decide it should belong with. So when you hear somebody ask, well, which is bigger, kilometers or meters? Okay, which is a really irritating question. If you knew which one was bigger, would you have screwed up the calculation? No, you didn't know which one was bigger. That's why you needed help. Okay, so be very careful with your placement of your powers of 10 and how you run your calculations. Okay? They are related to each other. It allows for certain cheats, but at the same time, those cheats can backfire because it requires extra information. Which is bigger or smaller? And if you know which one's bigger or smaller, great. Your brain's better than me. Okay? And there's lots of people that have better brains than me, for the record. We talked about our fractional notations, so we won't worry about that. Classifying our chemical reactions. Which of those chemical reactions have we talked about?
Single and double replacement.
We've talked about single and double replacement? We actually haven't covered single replacement reactions. The other ones we have. So single replacement is the last reaction on our list that we have to address. It becomes an extra challenging one because all sorts of fun stuff hits the fan. What's that fun stuff? Be careful. That's the oxidation state that you watched over the weekend. Did you not watch that over the weekend? This is going to be a really rough lecture. Even if you watched it, it's probably going to be a really rough lecture. So let's take a look at our single replacement reactions. Just like our double replacement, we are expected to predict these. Okay, so we're going to come up with some simplifications to help us get through this process. So it is going to remove some chemical understanding. That's okay. But let's take a look at that equation. I need to be able to predict what the products are. Right? So I need to look for patterns. What patterns do you see? Checkered? Chevron? Somebody laughed. It was a really bad joke.
There are metals in there?
You are acknowledging that zinc and lead are metals. And that sulfate, I'm going to be better with color coding, and that sulfate would be a nonmetal. If we compare that back to our general equation, what do you think is going to happen then? The metals are going to switch. It does not have to be the metals. The metals are our default, the easiest ones to go through and do. So let's go ahead and do that switch. What do you predict as products?
Lead and then plus the sulfate.
Lead and then plus zinc sulfate. So there's a couple big pieces that we're going to need to attach into this. First and foremost, phases. When dealing with the single replacements, this is going to be one of those cheats. We copy the phases that we had from the reactants, which means if lead is now by itself, its phase is just like zinc by itself. So lead's phase is solid. Zinc's phase will be, or the zinc sulfate phase will be aqueous. How would we know the zinc sulfate was aqueous? Like no. Say that again? Look up the rules for SO4. What rules? Our solubility rules. We could pull up our double replacement solubility rules and verify that zinc sulfate was soluble. Okay, which I think it is. Okay, the next thing we've got to do, did we actually predict these products correctly? Lead is all by itself, so do we have to balance it with anything? Do we have to balance it with anything? No. So our first step is look at the product. Is that product a valid thing? Okay. If it is, good. When you're saying yes, you were probably saying you wanted to balance it against the reactants. We aren't there yet. We're at step 1 in balancing chemical reactions, which is make sure your products are correct. Okay. How about zinc sulfate? Is that one correct? How would I know? Good question. What do you need to do?
You gotta memorize the N is +2.
I told you that you should memorize that zinc in an ionic compound. How do you know it's an ionic compound? Metal. Is it a metal and a nonmetal? Yeah, so zinc in an ionic compound, which it is a +2. So clearly it's balanced. No, okay. What else do we need? We would need to know the charge on sulfate. What is the charge on sulfate? How do you know it was a -2? I told you to memorize that. Why did I tell you to memorize that? So that you could solve this question faster than someone that had to look up all those answers. That's why we memorize. Shortcut the amount of work we have to do. Okay? Efficiency. Do those charges balance out? Yes. So when we're predicting, we have to predict products that have 0 charge. So those charges would cancel, which means zinc sulfate is a perfectly fine product. Okay? Now the next question. Is the equation balanced? We have to go through it? Fair enough. Fine. Not happy about that, but that's fine. I don't have to be happy, right? How many zincs do you have on the left? How many, and on the right? Sorry. How many leads on the right? And on the left? How many sulfates? 1 and 1. Am I okay balancing it as sulfate? Why? Because it stayed as 1 unit. Okay? It's sulfate on both the left and the right. I can balance that as one piece. If you don't like that, that is quite all right. How many sulfurs on the left? 1 and 1. I think I heard a 4 just to check. This 4 applies only to what is directly in front of it. What is directly in front of it? The oxygen. So there's 1 sulfur. How many oxygens? 4 and 4. Is it balanced? Cool. We doing better with balancing? Ish. That's good enough. Okay. This happened this morning, so it was kind of cool. What we've done with a chemical equation is we are now predicting what could happen. Okay? Has any of you imagined what you could do if you won the lottery? I wouldn't be in this class. Thank you. I appreciate that. Okay? I've actually imagined it. I would still be here. Okay? But one of the things that I've added to it based off of this morning's conversation is that what I would add to that is every class I would show up in costume. Just because I thought that was awesome. Okay, so if I win the lottery, I'm going to show up to class in costume. Do you expect me to show up in costume on Thursday? If I win the lottery, I have a plan on what could happen and what would happen, if it did happen, what I would do. Does that mean I'm going to do that? No. Sorry. Okay? So a chemical equation is that plan. Single replacement adds a whole nother layer to this. In this single replacement, we have to decide, did that plan actually come to action? Does that reaction actually occur? If we think about how we did our double replacements, we looked for changes in phase. We specified the phase kind of arbitrarily. We just said it just copies across. So we can't use that phase information. We need something else to help us trigger and decide, did that actually happen? In the case of the single replacement, what do we need to have access to? Oh, geez, come on. What we need to have access to, and I'm hoping that eventually the computer catches up with it. Oh, for the love of monkeys. A list of metals. Is it just a list of metals? Okay. It's an activity series. What is that activity series in reference to? It's in reference to the ability for this reaction to occur. Okay, so what I have to do is pull information from my equation and find it up here. That's a list of metals, so what should I look for? Zinc and lead, so there they are. So now I have to be able to interpret what this means. Okay? The higher up on the activity series, the more active you are. This is bad mojo, but just work with me. If you were more active as a person, what might you describe, or how would you describe those encounters? Aggressive? That's okay. Would you be around more or less people? If you were more active. If you were more active, you would be around more people, right? So the higher up on this list, the more active they are, the more likely we will find them with other things. That's not where I was going at all. I'm glad that didn't get recorded, I hope. Jeez. Zinc is more... That's horrible. Zinc being more active should be found with more things. What are our things in chemistry? I'm just going to walk the other side of the classroom. What are our things in chemistry? Elements. Where is zinc found with more elements? In our chemical equation. You're like, I have no idea what you're talking about. Do you see zinc here? In that black box? Yes. Is it found with other elements? No. So there's no other elements. Do you see zinc in here? No. So that's a dumb one to look at, right? There's not even zinc. Let's move to the next one. Do you see zinc in that one?
Yes.
Is it with other elements?
Yes.
Yes. So it's with a lot of stuff, right? So with stuff. Okay. How about the next one? There's no zinc, so irrelevant to look at. Where is zinc with stuff? In the product side of the equation. So let's go ahead and underline that because that's important. Okay. Let's take a look at the lead. The lead being less active is going to be what? If you are a less active person, are you expected to be found near more people or less? Less people. So lead being less active should be found with less people. First one doesn't make sense. Let's look at lead sulfate. What is it with? With stuff. Look at the far right. With nothing, right? Where is it found with less stuff? In the product. So if I mix those reactants together, what happens? Zinc sees the lead and goes, I want to be with stuff. Give me the stuff. Lead, on the other hand, is like, I don't want to be with stuff. Take my stuff. And what do we get? Zinc with sulfate and lead by itself. We now have a chemical reaction. You're like, is it really that simple? Yeah. Don't believe me? That's okay. You've got practice. Okay. So you've got 3 more questions to practice. See what you can come up with those. If you got questions, raise your hand. I'll come to that second one. We started it out. We got a lovely process going on. Nickel's by itself. It does the exchange. We get the magnesium with the nitrate. Okay. There was a crappy job done by somebody who didn't write the phase up there, so they ignored it, but that's okay. Let's just say it's aqueous. It is aqueous because it's with nitrate. Okay. And then there was this question, which is understandable. What about that 2? Right? Okay, for those people at home, that red 2. What does that red 2 mean? It means there's 2 of whatever's directly in front of it, which would mean the nitrate. So it means there's 2 nitrates. Where are there 2 nitrates? Touche. In the parentheses, yes, keep going. They're reactants. We can go more. There are 2 nitrates where? Are the 2 nitrates with magnesium? Are they with lead? No, they're with nickel, right? Okay, so there's 2 nitrates with nickel. Okay, and so where I bet this question is coming from is now that I've done the swap, should I write a 2 over there? Okay. It depends on your explanation on why. Okay? If your explanation on why is because there's a 2 over here, that I should write a 2 over here, that is wrong. Okay? Now why? Why did I write this initial 2? To balance nitrate with nickel. Is nitrate with nickel anymore? No. So I can't put the 2 there for the same reason because it's not the same compound. Okay? And this is where things are going to become really fun. You're going to be like, but isn't the answer the same? The answer may be the same, but the why becomes important because when we change the question, it may not be the same. So you have to understand why these numbers come into play. Okay? Do I need that 2? Why does that purple 2 have to exist? Okay. So we'll get two common answers coming. There's still two nitrates. The nitrates need to balance, two on each side. That's actually irrelevant. That has nothing to do with why the 2 is there. The 2 is there because magnesium is a +2. Nitrate is a -1. How many nitrates do I need to balance magnesium? 2. That's why the 2 is there. And for those of you keeping score, we have a 2 as a subscript outside parentheses with nitrate in the middle. That 2 is entirely different than the 2 outside the parentheses with nitrate inside it on the other side of the equation. They mean entirely different things. But they are written in the exact same location, and it is very easy to confuse them. So be careful that you know why you're writing the numbers where you're writing them. Okay? And that is a challenging thing to work through. Ultimately, when do you learn that? When you do enough practice problems that your logic breaks and you fail at it. Typically when that happens is during the exam. We're pointing it out now, so hopefully that doesn't happen. Make sense? Kinda? Okay, some people said yes. That's good. I want to address one more thing, because this was another interesting observation. Whoops, I didn't mean to erase the 2. Why not write MgN2O6?
Because that's not nitrate anymore. Because it applies to the nitrogen.
Well, the 2 applies to the nitrogen and the oxygen. So I'd have 2 nitrogens and 2 and 6 oxygens, right? Is it clear I have nitrate? No. So we don't want to multiply that through in our formula because it removes some information. It removes the information that we have the complex ion nitrate. So don't condense those. Okay, I understand why you want to do it. Don't do it. So far, so good? Did it happen? Like, what do you mean, did it happen? Did this reaction occur? How do we know that? We look for the magnesium. That's an eraser. We look for the magnesium. We look for the nickel. Magnesium's higher than nickel, which means that magnesium is more active. Where is magnesium found in a compound? Product side of the equation. That reaction occurs. Yeah? Okay. How about the next one? Silver with the chloride and then aluminum by itself. I think I intentionally goofed this. Anybody looking at that being like, but?
Yeah.
What are you butting?
Aluminum has a higher activity.
Too advanced. Don't but that yet. So nobody else is looking at that being like, that's wrong. Does that match the general format that we showed above? No, okay, so you're saying it's wrong because of that. It doesn't match the format. Does the order in which I place those matter? No. 2 plus 3 is? 5. 3 plus 2? 5. The order in which I do that doesn't matter, so don't stress about that. Okay? Did I draw the proper formulas? No? What needs to change? It should be AgCl3? Yeah. Why is the 3 next to the chlorine and aluminum chloride? You need to balance the charge on the aluminum. What is the charge on silver? You're like, I didn't memorize that. You should. That's one of the ones I told you to memorize. It's +1. What is the charge on chloride? -1. Is that formula balanced? Yep. Writing the 3 next to the chlorine is wrong. Is the equation balanced? No. How do we fix it? I'm getting funny looks. So how do we make sure we balance it? Silver's on the left. Silver's on the right. Chlorine's to the left. Chlorine's to the right. How do we make that a 3? Oh, that's what Mike just did. Cool. Okay. Aluminum's to the left. Aluminum's to the right. 1. We've checked them all. Whoops. So we erase it all and we try again. Silver's to the left. Silver's to the right. Does it balance? How do you fix it? Everybody seeing it now? Okay. Some of that should start to become reflexive where you don't have to show work. Okay. By next week, hopefully Thursday next week, it is reflexive and you don't have to show work. Okay. If you have to show work, that's okay. It's not the end of the world. It's just going to take a little longer. We good? Did that equation work? Do I get to show up in a costume? How do we decide? Silver is Ag, aluminum. Which one is more active? Aluminum. Where is aluminum with stuff? On the left-hand side of the equation. Which means when I mix silver solid with aluminum solution, guess what? Aluminum's like, I want my stuff. And silver's like, that's cool. Which means nothing happens. Okay? That's how we read the activity series. Anybody notice anything interesting about the activity series, in particular the bottom of the activity series? Bottom? Gold? Platinum? Silver? What can you tell me about those? I heard a couple things and I wasn't quite sure what everybody said. Let's try that again. What are they? The most valuable. We use them in jewelry. Okay, why? What does gold do? Being the least active, what does it want to do? Be by itself. Imagine you put on jewelry and what did the metal want to do? Be with something else. What does it do? It melts your hand. That's not good jewelry. Just for the record. We make jewelry out of gold because what gold does is it just sits there. Okay? We literally made the most valuable thing that we know in jewelry useless. It does nothing. Okay? So we use jewelry out of it so it doesn't react with us. That's useful. What else do we use gold for? Wires, yeah. Fort Knox, anybody? What's the whole point of Fort Knox? Currency. Gold, platinum, silver, all of those things are used as currencies. Why would we use them as currencies? They don't change their properties. Which means if I have 500 pounds of gold, in 2 years I will have 500 pounds of gold. Okay, it doesn't change. Now I can base a currency system off of that because it doesn't matter how many times that exchanges locations or who cleans it or washes it, it stays gold. Imagine if we switched it up, instead of gold, we had lithium as our currency. Lithium is so high on the activity series that it reacts with water. You could literally attack Fort Knox with water balloons and water guns, and the entire economy goes up in a splash of water because it dissolves and melts or dissipates through the floor. Okay? So we picked a currency system that literally doesn't react. That's kind of neat. The activity series explains the world economic system. Close enough. Okay? So, the activity series is something that I don't expect you to memorize. I do expect you to use it. Okay? How much should you use it? Well, it depends which activity series you're given. You may have to dig for an activity series online. You may have to dig for an appendix in your textbook. Okay? All activity series have differing amounts of materials within them, so you have to think about looking for other ones. When it comes to the exam, I'm not going to give you a massive one because it takes up too much paper. So I'll give you a small one. That small one will have just enough information to answer the question that you need. Okay? With probably a few other random things just to mess with your head. Because we have to. Okay? Kind of, sort of? Close enough. You don't complain. So yeah, that last one, what happens to that last one? It doesn't react. Yep, it also doesn't react. Active metals, some metals are so active that when you add them to water, they react with water. Okay, technically what they're reacting with is not water. What are they exchanging for in water? What's the metal in water? You're like, there isn't a metal in water, but hydrogen can act like a metal. You're actually doing an exchange of hydrogen for sodium. Okay? And that's what's happening within that reaction. That's your active metals. Becomes sodium hydroxide. You're pulling a single hydrogen from water. So it's better to represent this as actually HOH. And I'm going to double back to this because I really don't want to talk about this, but I know you're in lab, and let's help clarify some things. In lab, you're going to be proving an activity series. Depending on who your instructor is, they may be more or less of a jerk. If you have me, I'm a jerk. If you don't have me, they might be nice. Okay? Yes? Why is hydrogen all in caps? What is different about hydrogen in comparison to everything else up there? Hydrogen's a nonmetal. Hydrogen is also the thing that's used as the 0 point for everything else. Okay, when you look at a more advanced form of it. That's why it's all in caps. So when we look at your lab today, what you're going to be doing is taking a variety of solids and solutions and mixing them with each other. So for instance, we're going to mix magnesium with nickel nitrate. Okay, and we would expect a reaction. Or we would predict what could happen. Magnesium with nitrate. Yeah? Close enough? Yeah. Cool. One of the things that makes the lab more challenging is that what we give you instead is we say this. Now what happens? What's the difference? The charge is now all of a sudden specified. So when we go through the single replacement, what's going to happen? Same thing as it did in the other case, except now the charge is exchanged. Magnesium is going to become an ion. What is the ion form for magnesium? A +2. What happens to the nickel? Just becomes a solid. So we could write the equation in this format, or we could write the equation as we initially studied. Okay, why point this out? What do you guys think? Say that again? Okay. It is going to eventually drag to redox reactions to help see this. The other thing that I'm pointing it out for is that when we talk about it in class, we're talking about it with the neutral structures. And we said are more and less active, we're more likely to be paired with something, right? If we take a look at the lab equation, do you see it paired with anything? No, so that makes it more challenging. Okay? Either format is okay. One is known as a molecular format, one is known as an ionic format. Okay? If you write things in the ionic format, we can't use the pairing with something else, can we? So we need a different system. What's that system we're going to use? The higher in activity, the more likely it is an ion. The lower in activity, the more it's just an element. So the higher in activity, you can be in a compound or an ion. And the bottom one, you'll be in an element or by itself. So there's two different ways to interpret that depending on how you want to write the equation. Kind of, sort of? Okay. The extra layer that I literally don't want. So, continuing. Dang it. I wanted that equation to point out oxidation and reduction. So real quickly, write that reaction again. We had magnesium plus nickel ion to go to magnesium ion plus nickel. What happened to the magnesium?
It lost 2.
We started with no charge, which means the balance of protons and electrons was equal. That's why there's no charge. When we go to the product, what happened to it? It had to have lost 2 electrons, and that's why it became positive. That loss of 2 results in a positive charge. Well, where did those electrons go?
Let's give it to the nickel.
The nickel, if we look at what happened to the nickel, started as a +2 and it ended as a 0. So the nickel gained those electrons that magnesium gave up. And in an equation like this, it's not a big deal because everything balances out nice and pretty and neat. But what happens if we change that? Of course, now the equation won't work, but whatever. To potassium ion to potassium metal. Is this equation balanced? Okay. So some people will say yes, some people will say no. And a lot of that is relying on how much you've really absorbed the content that we've looked at. If you've just focused on getting the bare minimum down, I don't blame you, that's good. You're getting that bare minimum down. When we balanced, what do we balance based off of? The number of atoms on each side, right? How many magnesiums? Magnesiums. Potassium? Potassium. So it's balanced, right? But what did we not properly take into consideration? The charge. Why does the charge matter? What contributes to charge? Electrons. Are electrons matter? Yes. Is our charge balanced? On the left-hand side of the equation, we have a +1 charge. On the right-hand side of the equation, we have a +2 charge. The charge didn't balance out. That means there's an electron doing something somewhere. Okay? That is not a properly balanced equation because electrons aren't allowed to go into the equation. Why does this become exceedingly difficult for us to see?
Can't see the electrons.
Okay? Some people are wondering, you can't see the electron. Not only can we not see we couldn't see the atoms either. So really what you're saying is it's not that we can't see the electron, it's that we don't write the electron in a balanced equation. Why not? Electrons are incredibly unstable. They are so unstable that they can never be found on their own, which is a good thing. Because if they could be found on their own, what happens when you're walking down the hallway? You get electrocuted because you encountered a bunch of random electrons just chilling out. That's a problem. Okay? So electrons don't exist on their own, so we need a way to explain what's going on with those electrons. That's the idea of the oxidation and reduction chapter. That's its whole point. Okay, is trying to address that. So when we look at it, we get oxidation and reduction. Okay? And the difference there is looking at that balance of electrons in a reaction. Reduction and oxidation is the transfer of electrons from one thing to another thing. That thing could be a molecule. It could also be an atom. If it's an atom, we might call that oxidation state, the balance of protons and electrons. If it's a molecule, we might call that charge. They're referencing the exact same thing. And I don't know about you, but there we go. Stop it. Okay? We're looking at the balance of protons and electrons in both cases, oxidation state and charge. But the charge applies to all things, which could be an atom, it could be a molecule. Oxidation state very specifically applies to a single atom. Okay? The analogy that I've been using that seems to work fairly well is, do you have a budget? What's a budget? You should figure that out sooner rather than later. Okay? Is there a certain amount of money you can spend per day? So you go like, no, I can spend whatever I want. You could drop 20 grand right now. No, okay, so you have a budget. Okay, you have a daily budget. There's an amount of money that you can spend in a day. Is that the same as your annual budget? I kind of hope not, right? That would make the rest of your year really painful. Okay? That comparison of the part versus the whole is the same difference between charge and oxidation state. Charge is your annual budget. Oxidation state is your daily budget. Right? That analogy does fall apart, but it gets through most of it. Right? So when we go through and look at these things, we have to recognize that balance and how it changes between those different systems. There are rules associated with these. Okay? To these rules, I would argue there are 3. Probably the most important is that oxidation state for oxygen is a -2. Okay? That means when I bond oxygen to anything else, it will take 2 electrons. Why would oxygen always take 2 electrons? Other atoms can balance an octet too. So balancing the octet isn't bad. Isn't a bad answer, but it doesn't explain the observation. What is a characteristic of oxygen?
It's always in pairs of 2.
It's pairs of 2, but so is chlorine, bromine, iodine, oxygen, nitrogen, and hydrogen. Oxygen is an exceptionally electronegative element. What did electronegativity mean? The ability to take electrons from other atoms. Oxygen will always take 2 electrons from other atoms. Because it has a high electronegativity, it will do that. There are 2 exceptions to that. What are those 2 exceptions? Nitrogen and oxygen, or hydrogen, don't count. Oxygen is more electronegative than both nitrogen and hydrogen, and it will take electrons from both of them. Fluorine. Fluorine is more electronegative than oxygen. When I bond fluorine to oxygen, what happens? Fluorine takes the electrons from the oxygen because fluorine is more electronegative. There's one other exception. Chlorine's lower in electronegativity. Which is stronger, oxygen or oxygen? They're the same, which means if there's 2 electrons between them, what happens to those 2 electrons? They split. One goes to each. The oxidation state won't be -2 because that says one oxygen was stronger than the other. Okay? So those are the 2 exceptions. Okay? So ionic compounds, you need to know the charges from your ionic compounds, how those things split, because that gets you a charge. With a charge, you can get oxidation state. How do you get that? You solve it. The charge is always given to you in your upper right-hand corner. Okay? The sum of each of the elements' oxidation states in that unit will then equal the overall charge. Okay? Guest lecturer coming in the back door right now. 2 people looked, that's good. It was a joke. What is the oxidation state of the iodine? How do you know it's a -1? You looked at the periodic table, which means you're looking at the ionic charge. Where is iodine in an ionic compound in that equation? It isn't, which means can you use the ionic charge iodine? Nope. What's the oxidation state of the iodine? Okay, I've got a 0. I'm going to be a jerk and say you're wrong. I could also be really nice and say you're right. Why are you saying it's 0?
What is the charge then if it's not?
I did not ask for the charge. I asked for the oxidation state. The oxidation state is something that you always have to solve for. Okay? How many times does iodine show up in the equation? Twice, which means you have to solve for it. Twice. Which one do you want to solve for? Left or right? Left. Okay? How do we solve for it? This is that formula that nobody likes. That's okay. That formula should be really familiar. That formula is what was given to you in nomenclature. And if you followed that formula in nomenclature, it becomes easier in oxidation state. If you decided to not follow that formula in nomenclature, oxidation state is not very nice to you. How many iodines are there in that compound? 2. What's its oxidation state? You don't know because you have to solve for it. X. How many oxygens are there? 5. What's its oxidation state? How do you know it's -2? Because I told you so. What's the charge? There was a cautious 0 there. What do you mean? Why cautious? Where's charge specified? In the upper right-hand corner. What is in the upper right-hand corner of that compound? Nothing. What is the symbol for nothing? 0. Are you cautious anymore? No, it's 0. Can you solve this equation now? 2x minus 10 equals 0. Add 10 to the other side. 2x equals 10. Divide both sides by 2. What do we get? X equals plus 5. Wow, I even got a ding with that too. Plus 5, there it is. Somebody starts doing that intentionally. Bonus points. No, just kidding, don't do that. Okay. Somebody also said that the charge on the or the oxidation state on the iodine was 0. Were they right? Were they right? Now you're all like, you're a tricky little, yeah?
I don't like answering questions.
Wouldn't it be plus 5? What's the oxidation state on that iodine? 2 times, do you have to solve for the oxidation state? Yes, always. So 2 times X, what does that equal? The overall charge, which is 0. What is X? 0. When that person said iodine was 0, were they right? Yes. Where were they right? On the product side of the equation. That was about 5 minutes to solve those 2 math equations. You got to get a lot faster. Sorry. Because you need to be able to determine the oxidation states for all of those elements. Every single time an element shows up, you have to nail that oxidation state down. Once you've got that, you can now identify that that reaction was a redox reaction or a reduction and oxidation reaction. How do we know that? Because the oxidation state changed. When do you have to do that? Typically when you're asked, is it a redox reaction? Okay. Other than that, you don't have to stress about it. A lot of people have a hard time with this. You're looking at simple algebra a lot of times. So there's a lot of repeated calculations, but they're relatively straightforward. It does take time. You have to watch for it. If that was all it was, that would be too easy, right? We always like things more difficult than that. So we have to decide what happened to the iodine. It went from a plus 5 to a 0. What happened to the number? It went down. So of course we would say because it went down, it gained something. Damn it. Why did it gain? True, we can't gain protons, but going from a plus 5 to a 0 wouldn't be gaining protons either. We can't lose protons. The only thing we're allowed to exchange are electrons, and electrons are negative. Remember how I said that negative sign is a pain? Ta-da! What happened to the oxygen? God, that was an awful lot of words to say that -2 to -2 was nothing happened. What happened to the carbon? It lost electrons. Anytime you have an oxidation, guess what? You will also have a reduction. Why? If something is oxidized, it lost electrons, which means the electrons go off as products. Can electrons exist on their own? Nope. Something must absorb them. Because that something is absorbing them, we now have a gain. Okay? So the gain and the loss will have to happen at the exact same time. Okay? So now to more stuff, which was all in the video, so maybe it's not a big deal to yell about. We want to define what those terms mean. Loss of electrons is oxidation. Gain of electrons is reduction. Why are we defining those? It comes from history. Oxidation and reduction were defined well, or explained in reactions well before an understanding of electrons' existence. Okay, really? I built a boat. The boat sunk after a couple of years because a hole developed in the iron. Why was there a hole? Rust. What happened in that rust process? The iron was exposed to oxygen, which means it must have oxidized. That's where the word is coming from. Okay? Reduction is just the reverse. Oxidation is the increase of oxygens. Reduction is the decrease, hence reduced. The name makes sense. That's where it's coming from. The reduction of oxygen to the compound. Is that really true? Let's go ahead and take a look. Iodine gained electrons. It was reduced, right? Reduction means loss of oxygens. I2O5 becomes I2. What happened to the amount of oxygens? It was reduced. Look at that. That's kind of cool, huh? It went down. Ta-da. What happened to the carbon? It was oxidized. How many oxygens does it have? 1 to 2. We increased the oxygens. Oxidation. Okay? Leo says Gur is my personal favorite, which you already heard in the play posit video, and I won't rip on biologists any more than I have to with the oil rig or oil rig. Literally, come on. Like, really? Oil rig, biology, study of life, and you're literally using the study of death to explain your reactions. Leo's a freaking lion. That's life. Just, shh. I'll calm down. I won't, but. If that was not enough, we also introduced this concept of agents. Okay? Why would we make this even more complicated than we have to? Because of the English language. Okay? That's what I blame for this. When we're talking about oxidation and reduction, those are describing the process. An agent is describing the species. So it's getting more refined in what we're talking about. So an oxidizing agent is the thing that caused something else to be oxidized. So if I'm an oxidizing agent and I cause you to be oxidized, what happened to you? You gained oxygens. We could do that. You lost electrons, right? Oxidation. Where did you lose those electrons to? To me. So what happened to me? I gained electrons, so thereby I was reduced. What did I say I was to begin with? The oxidizing agent is reduced. The reducing agent is oxidized. Okay? It's describing what you're doing in each of those processes. You will see it, if you see that ing, you should probably just skip it because, it's just confusing. Okay? If you see that ant, it's also a red flag that you're looking at something like this. It's describing the identity of that species. If that species is causing something, it is now the oxidizing agent or an oxidant. That means it was reduced. Why do we need these labels? If I'm going to store chemicals, I have to put them in a cabinet. I'm not looking at a chemical reaction. I'm storing that, waiting to do a chemical reaction. If I have a chemical that is an oxidant, I probably don't want to put it next to a reductant, because what would happen? Kaboom! So if I have a way to identify the species, I can keep them separate from each other without actually having to look at the chemical reaction. That's why we have those labels. Okay? You've got a lot of examples to go through and look at. I'll leave you to go through and look at those. I expected to talk a whole lot faster today and horribly bombed on that, so we'll just have to pick that up Thursday.